It's our pleasure to have Gursharn and Kaur, and who will be talking about fluctuations on dense random graph models. Please go ahead.
Thank you, and I would like to start by thanking all the organizers and also to invite me here. This is a very wonderful place and a lot of interesting talks that I'm getting to attend. So this is a work on higher order fluctuations. This is a joint work with Adrian Roellin, and he talked about this in his talk yesterday. So I'll begin by defining what the subgraph density means, and just going over just to fix the notations, explaining this again. So consider a dense graph G on n nodes. Then for a finite simple graph F on k nodes, the subgraph density, this density of F in this graph G is nothing but the number of injective homomorphisms of F into G divided by the total possibilities here. So here we want this scaling is basically to make sure that the subgraph density TF of G is always between 0 and 1. And if you have a graphon, then which is a symmetric measurable function from this unit square to 0, 1, then you construct a graph by first selecting these node features uniformly at random from 0, 1, and then connect node I and node J with probability kappa. So we call the kappa, we will use the notation kappa for our graphon, as Adrian also used in his talk. You'll see why, because we are using W for something else. So GN is a graph where you have n nodes and node features are selected uniformly at random from 0, 1. And then you connect I and J with probability kappa of Uij. Then similar to the subgraph density we defined for a given graph GN, for a graphon, when you construct a graph GN, you have the expected subgraph density of F in GN is nothing but this k-fold integral of the product terms, which is also, so we call this TF of kappa. For instance, for edge density, this is integral that of kappa xy, such that one node is connected with feature x is connected to another node with feature y. And similarly for triangles, we have x connected to y, y with z, and z connects back to x here. Now the dense graph convergence theory by Lovatz and Segedi says that if you have a sequence of dense graphs Gn, so here Gn is a graph on n nodes or an increasing sequence of dense graphs, then you call this a convergence sequence if the subgraph density for every finite graph F converges to something. If all these sequences have limit, then you say that the sequence of dense graphs converge. And what we have, and the limiting quantity, limiting object can be characterized by a graphon, which is a function from unit square to 0, 1, so that all the limiting quantities can be determined by this graphon. So, and conversely, if you have a graphon, so that was one way that you have a sequence of graphs that converges and there is a limiting object, which you call a graphon. And conversely, if you have a graphon, there you can construct a sequence of graphs that I just did in my previous slide, that you choose this node labels and connect them accordingly, according to kappa, then that sequence converges. So for every graph on kappa, there exists such a sequence. And that converges through the quantity that we define for kappa, TF of kappa surely. Right now, let's consider this favorite example for everyone here, which is the Erdos-Cheney random graph. You have a kappa to be a constant graph on P. And in that case, the sequence of dense graphs converges to a constant graph on P, with the expected density of any graph F to be equal to the P to the power of the number of edges you have in that subgraph F. Now, as Adrian mentioned in his talk yesterday, that this is only a first order limit theory. You only know about the convergence. And the next obvious question that one would like to ask is if there is a center limit theory here. Now, because the first order limit theory is given in terms of the subgraph densities, one would expect that the fluctuations can also be expressed through the subgraph densities. So you basically want this CLT results for your subgraph densities. But there's a bottleneck here. There's some challenge here. So if you look at this, this was explained in Adrian's talk yesterday as well. If you have a sequence, Erosionic graph, then all the fluctuations are dominated by the fluctuations in the edge densities. They are all governed by the edge densities in your Erosionic type graphs or for a constant graphon. Now it becomes even more challenging when you have a general graphon. So if in case of Erosionic graphs, these node labels were really not important. You were just constructing edges independently. It was like tossing a coin without worrying about the node labels or features. But for a general graphon, this is even more difficult because all you have is that the fluctuations are all dominated by something which depends only on the node labels. Unlike the Erosionic case where everything was determined by the edge densities. So if you just work with the subgraph density, then every time you just come here and you get stuck, you don't get anything much more here. So you definitely need something more. So we go back and look at this work of Janssen and Nowicki, which defines the generalized U-statistics and their application for random graphs. So just to define the generalized U-statistics, let's say you have a function f from Rk cross Rk choose 2 to R. So Rk choose 2 is all possible K choose 2 combinations for your index sets. So you have this pairwise dependence also in the variables here, and not the variables, it's arguments. Then the generalized U-statistics. So without this K choose 2 or K choose 2 or the Y arguments here, this is just a classical U-statistics, standard U-statistics. We call it generalized. So Janssen and we call it generalized. If you also include with this individual nodes or the labels, you also have this pairwise interaction terms included in your function. And how they are useful for random graphs is from our construction. Let's say you have U1, U2, Un be the NIRD vertex labels and YIJs be the edge indicators. Now, you can define the subgraph indicator in the following way. So you can define this function f, which depends on this k vertex labels I1 to Ik, and these edge indicators. Actually, it doesn't just depends on this vertex indicators, vertex labels. It's just a product of these edge indicators whenever your vertex v and w are connected in f. So this gives you an indicator. This is 1 if you have a copy of f on this set of nodes I1 to Ik, and it's a 0 otherwise. So what this generalized U-statistics, if you define this for this function f, this gives you, this is something like a number of copies, but it's a bit different from the way we define the homomorphism, our subgraph density, but it's more or less the same. So the only difference is that we are looking at the k tuples with no repetitions, but here it's a bit different and this scaling is a bit different. But in a sense, this is how you use this generalized U-statistics for random graphs. Now, what's the advantage of U-statistics? So even when we didn't have a generalized U-statistics without this interaction variables, the U-statistics, when you have this function, you can go back and so even without this interaction terms, this U-statistics has a very nice decomposition called the Hofting decomposition. Now, what Janssen and Nowicki show that the generalized U-statistics also has a very nice decomposition. But what they have used is that they want these YIJs to be their independent variables, which may not be the case for a general graphon, because there is a node dependence for each interaction Ij and Ik. There is a common vertex label Ui sitting, which makes Yij and Yik dependent. They are not independent anymore. But nonetheless, so this is one of our main contribution, or the idea is more or less coming from Janssen and Nowicki's work, that the subgraph densities have a decomposition of the following form. So here, this is a function. This is a quantity, not where this node indicators or labels U depend only through H union A, and these are the edge indicators which depend only through H. So you are summing over all possible subsets of summing over all possible subgraphs of F and all possible subsets of the node set F. I'll give an example, it might be clear more. Such that these terms that you have here, they are orthogonal, they are pairwise orthogonal. So what do we mean by pairwise orthogonal here is that whenever you take two different copies of H, in the sense that they are not isomorphic, or if you have this node subset A, such that they are not equal in cardinality, the number of nodes are not the same, then the covariance between the two terms that you have, HA or H prime A prime, is 0.
I have a question on this. So you could have instead of choosing edge indicators, you could have chosen Yij to be uniform in 0, 1, and then define your function by saying that W of xi, xj is smaller or equal Yij, and then you would get the independent y's. So would that be a way to prove this?
No, yeah, that wouldn't be a problem. You can define Yij's that way too.
Because then you have the independence you need in the Janssen theorem.
Yes.
So how come people don't do that?
No. So so I'm not saying that we are doing this only for the dependence case, or we are generalizing this. That's not what we are doing. So this is basically what Janssen and Nowicki have done. This is the idea is we are taking this idea from there. You're right that you can define this edge indicator so that they become independent. So we have this okay, so going back here, so we are decomposing the subgraph densities into this pairwise orthogonal terms here, RHA, such that whenever either the two copies H and H prime are not isomorphic, or if the number of nodes you have in the set A, they are not exactly the same, then the covariance is 0. Now, in fact, we do this exact computation and say that this R of HA are exactly of this form, where this there's a dependence on H only through the centered subgraph count. So we call this quantity centered subgraph. So this was without the centering. So you're subtracting the conditional expectation here, and we call this a centered subgraph count. I'll just come to that term here.
Question.
There.
I was gonna ask what is that.
This is this depends on what H you have and what F you're working with. I'll give an example, and it might be. It's a bit tedious to compute for a given F what chi would be, but so this is some. I'll come to that. Maybe the example will clear it. But you can find such a decomposition. That's what.
But your psi depends on all the uij's
Yes.
from J1 up to L?
Yes.
Because now it says UI.
No.
What does it depend
No,
on
so
exactly?
it depends. It depends. This is only a function depending on UI. Yes.
What is I?
I1 to IL. Is that
right?
That was my
Yes.
question. Okay,
Yes.
thank you.
Yes. So this I is a vector I1 to IL. So it depends. Psi function depends on all of these. This H union A, all these indices you have. And there is a scaling of 1 by square root n, choose L. So it's like n to the L by 2 here. So what this decomposition is basically telling you is that when we are looking at the CLT, or you want to look at the fluctuations here, the leading order terms, or these are the terms that are governing your fluctuations. And once there is once you see a leading term, then the other terms do not matter. So that's what was happening for Erdős-Renyi and the general graphons. Okay. Any other questions before I move forward? So just going back, so this is this is our main statistics, which we call centered subgraph indicators. We say that looking at this subgraph densities through this subgraph indicators, it's basically nothing. It's basically the centered subgraphs that are playing the major role here. And this this was this. So if we can show the normal approximation or some fluctuation results for these quantities that we have in the summands here, then you will get what happens for the subgraph densities. And this is our main result here now. I'll come to the example a bit later. I'll just state the result first. So our result says is that if take any d different graphs f1 to ft. So what we are trying to do now is prove center limit theorem for these quantities, for this quantities which are of this type, where you have the centered subgraph set indicators and they are weighted by this node labels and scaled appropriately. So we want to prove CLT for such things, which is exactly this. So, but what we have here is a joint CLT for any given graph f1 to ft, which are connected. Okay, so connected, we are only looking at connected because otherwise the density can be written as a product of connected components. So it's enough to look at the connected graphs here. So if you have f1 fd of on nodes k1 to kd, then for any sth graph fs here, if the size is only equal to 1, you basically don't have any edge. So there's no centered subgraph indicator in hand. You only have this functions depending on UIs. So just to make sure that the limiting normal distribution has mean 0, we just subtract this mean of this quantity. And otherwise they are, so these quantities are always mean 0. So you get mean 0 from here. Whenever the size is at least 2, you have at least one edge in the graph. So you get this. Then you combine these d quantities w1 to wd, and what we are saying is that this variance matrix w, so there's a normal approximation for this vector w, and let's denote the sigma to be the variance of this w matrix, and this is where we use w instead of using it for a graphon, which we call kappa. So as we mentioned last in the decomposition, that these two terms, that these terms are uncorrelated whenever this functions, whenever they are not isomorphic copies or whenever they are not exactly this two singleton nodes. So you see, otherwise you might see some positive. Sorry, this is non-zero only in this case. In every other case, these covariance terms are 0, and that's because what Adrian also mentioned, that when you have two subgraphs which are not isomorphic, then there is at least one free edge for which you get the covariance part 0. So with that, with this, what we want to now show is that the CLT for this vector w to normal standard normal, not standard normal, normal 0 with this variance matrix. So what we show is that this indeed converges. It has a normal approximation in the sense that when you take the supremum, so here we are writing it in these terms because we are using Stein's method. So when you take the supremum over this difference over smooth enough functions, so here P is the maximum, we can think of this as a maximum subgraph size that we have in the collection of our subgraphs f1 to ft, then this is bounded above by 1 by square root n. This is of order 1 by square root n. So this is only on this class of functions. which are p+2 times differentiable. They're smooth enough functions. And we want, if you are looking at the convex at distance between the distribution of W and Z, then this is of order n to the minus 1 by p+2.
So I guess in the context of, I guess, Bosworth's talk where there was degeneracy, so
Yeah.
would this limit be sort of not full rank normal distribution or something? Is that what happens?
No, so for us, these are centered subgraph indicators. These are the terms in your expansion.
Oh, once
Each
you've
of them
recentered
have
the
normal
coordinate.
approximation.
Okay, thanks.
Yeah, I'll come to I'll relate to what Bashwar talked about and with an example here. Adrian also talked about that example. Okay, any other questions before I? So there are two main proof ingredients here, as I explained. So one is decomposition for the generalized U-statistics, which says that the terms are dependent but uncorrelated. And the next main ingredient is the science method. How do you get the approximation for such sums where you don't have the IID or the sum, but so they are dependent but uncorrelated. So going back to the ortho, so I'll talk about these two things a little more and tell you how, just to give you the flavor how we arrive at this decomposition. So let's say so this was our subgraph indicator, right? So whenever I is connected to J in F, then this indicator tells you that there is a graph present on the set of given set of n nodes or not. Then you can write this as there is a decomposition. This is very simple decomposition that you take all possible subgraphs of H, which do not contain, not starting with an isolated vertex here. It must at least have one edge here. So it can be empty, but should not have an isolated node. So for example, and it is of this form. I'll come to give an example and then come back to this. So let's say you have just an edge. This is very simple. You can just add and subtract its conditional mean. And so this is where you have H to be the empty set. And yeah, so here you have H to be empty and H here has just one edge. Now, when you have two stars, it says that I is connected to J and I is also connected to K. Then also you can give this exact, so this is an exact equality. You can just keep adding and subtracting few terms and arrive at this decomposition, where this one is a full graph, this two-star graph. This one where you have the H is just the IKH, and this here your IJ is just the H, and this is the overall conditional mean. So this is what these terms. So now you can prove this by induction. So this is a simple lemma here, that you condition on this H, take the center subgraph similar to here, similar to what we are getting these terms here, right? And on the remaining graph, you take the conditional expectation. So H complement with respect to F here, I mean, H complement for not for, so whatever edges you have not covered in H, in F, only for those you are taking this condition. Any question? So now maybe before that. So this part is simple in the decomposition. And now the tricky part or the tedious part is to approximate these quantities, these product terms, by those individual UIs. So the next step is to give an orthogonal decomposition for these product terms, so that you get those phi of HA, psi of HA, and just the UIs. So here they are not yet, there's no orthogonal decomposition yet. For example, the stochastic block model, where you have alpha, so gamma is this threshold on the two communities, let's say. Then alpha is the probability that two communities are connected within themselves the first community. I mean, maybe just draw this. It's easier to. Alpha here, beta and delta here. That's our stochastic block model we are considering. Then for this, if you look at the edge density now, if I go back and look at the edge density here, so I only have two terms, but I also want this one to, I want to decompose this one as well further. So what we get here is that all these terms by getting the orthogonal decomposition. So here the kappa bar is just the overall expectation. And then this W is the indicator terms that UI is less than or equal to gamma. So this is specifically for the stochastic block model. And here the first term is of order 1 by square root n. The second term is of order 1 by n. Both these two terms are of order 1 by n. And the third term is of order n to the 3/2. So then this one, this graph has no edge or no node. This is just the overall mean. This one consists of one node label, and here this is an edge graph. So it's like you are decomposing this subgraph density into increasing sequence of subgraphs of the edge graph. And what Bhashwar talked about is whenever you're this rho 1, so rho 1 is you have exact expression for rho 1 for this particular example. Whenever rho 1 is equal to 0, then this is not a dominating term. Or when rho 1 is non-zero, then this is the dominating term. So you have the Gaussian limit here. So because we know that W.
So I now can re-ask the question I asked in Baswa's talk, sort of, because you have this nice formula. He never had the case where rho 2 is 0.
Sorry?
So what if rho 2 were 0?
Rho 2 was 0. Okay, so rho 2 corresponds to the chi-square term, but you still have this remaining. We show that this quantity also converges to normal when you scale it appropriately. So this one is normal. So if
I see. So whether rho 2 is 0 or not, you always have a 1 over n term.
Yeah. So this one, if this one survives, yeah, then you always have this 1 by n term.
Mm-hmm.
But there's no chi-square component if rho 2 is 0. And for instance, this last term that you have here, n to the 3/2, this is 0 for a constant graphon kappa, because you have beta equal to alpha here. Now, so this was about the decomposition. Now, little bit about the Stein's method I'll talk about, not going too much into details. So what we do is, any other question about the decomposition before I start about the Stein method?
Can I make a comment? A quick comment. What I might be confusing at the beginning. Can you go back all the way to the R values? There might be some typo that might have made things a bit confusing. One, yes, we're not deriving a normal approximation for the R's. The R's is just an orthogonal decomposition. They're uncorrelated, but the R's themselves need not, they can, but need not be normal. Maybe that's maybe a typo there.
So yeah, right. Sorry.
So the R's are just, the R's themselves are further decomposed into quantities that are normal. Right. They can be squares or sums of quantities that themselves are normal. Maybe that's just to clarify that.
Right. So these were your R terms, but you are basically giving a normal approximation for these statistics. Right. This not for this whole term, but just right. Thing. So okay, yeah. Any other comment, question? So how do we prove that? After you have a decomposition, how do you prove? How do you get the rate of convergence here? So we use the Stein's method. For the d-dimensional distribution, the normal distribution, the Stein's identity say that random vector normal Z, which has a normal distribution with mean vector 0 and variance matrix diagonal identity, then Z has a normal distribution if and only if the following expression holds. This is just a generalization of Stein's identity for one dimension. Here, this is a Laplace operator and this is a gradient operator. And so for every G, such that all these expectations make sense here. Now Stein's equation, so this is the main, the idea here. If you have questions about this, maybe Adrian is the best person to reach out. So a Stein's equation says that whenever Z is not exactly normal, but close to normal, you would expect this quantity to be close to 0. So what we are saying is that for a test function, consider f to be a test function, such that you equate these two quantities and find a function f, which is so we call the f to be a solution of this equation.
Is your little x now a random variable?
Not at this point.
So what are you taking expectation over then?
Z.
Yeah, but all the other terms have expectations as well.
No, at this point, we don't need expectation.
No, you should remove the first one and the second expectation. They should be.
Yeah,
Okay,
right.
yeah.
Not at this point. We don't have
I see.
expectation. So
Thanks.
later we find a solution and first find a solution and then replace it by a random variable, take the expectation. Right. Sorry, that's another type for here.
I mean, if x is a constant, it's okay to take expectations. There's nothing wrong with that.
So no typo. Okay. So with the Stein's method, what you want to do is you want to bound the absolute value of this term here, so that in return you get the bound on the left hand side. But you want to also replace before you start taking expectation and bound, you want to take W in place of X, for which you want the normal approximation. W is our candidate for normal approximation. Then we use the Stein coupling, which was introduced by Louis Chen and Adrian Roellin, and also Adrian worked with Fang Xiao also on this. So you call a triplet W. So just again recalling that our goal is to give normal approximation for W. Now we are finding a triple here of each of D dimension, such that this following expression, this condition holds. So if you can, for a given W, if you can find a W prime and G, such that this expression can be satisfied, this equality, then you call this a Stein coupling. Now, again, for all G, such that all the expectations here make sense. Now, how does that coupling help you with the Stein's method? Is if you have a Stein coupling, so and let's say you want this, so sigma be the covariance matrix, and you take D to be the difference between. So the idea here is basically that you want to take the Taylor approximation of a function at W around this W prime, which is not too far away from W. So this is the distance. So this is the difference between the two vectors. Then for any p plus 2 times differentiable function h, and z being the Gaussian random vector with covariance matrices, what we've shown that we want to bound this quantity that. So this is a complicated expression, but the idea here is that all these can be bounded up. These terms are all dependent upon the higher order moments of these differences D and the G term that you had in the Stein coupling. So once you know the bound for each of these terms, you can bound this left-hand side quantity. And so these alphas are just the vectors such that the total length is fixed, and these are all the derivatives and such things. Well, let's not go into detail. So the idea with this approximation theorem is that you can bound this quantity by something that's coming from the Stein coupling, using this coming from the Stein coupling, and also these functions h and all these constants. So the main objective now is if you can bound these quantities here for your given variables. So this is what we did, and find this over this class of smooth functions. So you need, for this one, you need p+2 times differentiability to get this result. And that's why we got only this p+2 order here. So just to summarize now, the fluctuations are for the subgraph densities are explained through the fluctuations in the subgraph, centered subgraph statistics. And the normal approximation holds even for non-constant graphon. And one more thing I forgot to point out here is that the node labels need not be uniform. They can come from any distribution here. You don't have to restrict it to uniform because you have already centered them, and the covariance matrix one can compute. So it doesn't have to be a uniform 0, 1 variable. So this is our main finding, that there's a decomposition, and then this is how there's a rate of convergence. And Adrian talked about the statistical applications, or whether a given testing a hypothesis that when you are given a stochastic block model, how do you test? Like what statistics you use for the with the CLT results? What statistics you use? Any other questions I can?
Questions?
So just to understand the Stein coupling part, the best case, which will most likely never happen, is if G is 0. Like what value of G would you be most happy with?
I don't know what, like for the optimal.
We can talk offline later.
Yeah. So we give it a choice of G that gives you the Stein coupling, and with that you can compute these moments here.
Right, but
like,
maybe if you put the G0, all of them, so ideally you would want G to be small, right?
No, if for Stein coupling you also have to make sure that the this relation holds.
Right.
Mm-hmm. So you cannot choose G arbitrarily as well.
Right.
So what is the G? What is the optimal, or what is the coupling that you use?
Maybe I can give you the exact thing. So when you fix a node, you have to remove the neighborhood effect from here. I can give you the exact expression later.
I guess the one question is like, I mean, how hard is this to push? Like all these expressions seem to hold even if you're in the slightly sparse regime. So what breaks down in this whole, suppose you had, I don't know, 1 over square root n times a graphon. That's your connectivity matrix, and you're trying to understand density of triangle squares and stuff. Which part breaks down? Is there any good intuition?
For sparse graph, I don't know.
Can I answer that question? As far as I know, nothing breaks down. It's just we were too lazy to do the actual bounding. As you can see from the expressions, you need to bound. So if you have if you have in the dense case, you can just upper bound, just absolute value upper bound. But in the sparse case, you actually have to calculate moments, which is much harder than just having supremum upper bound. So it's a matter of how hard you want to work to get a result. But in the sparse case, it should be we should be able to do it. It's just you have to work much harder. Yeah.
So by sparse case, you mean when you take this graphon to be some rho n times, rho n is going to 0.
Yeah, but for some subgraphs.
Yeah, in those cases, the variances will probably go to 0 or something of that sort. So
I mean, you soon get the problem that the number of triangles is less than the number of edges, and then sort of you can remove all triangles by changing only a fraction of the edges, and then none of that should work, right? Yeah. So it's sort of, if you have sort of high enough graphs, you can't do square root of n very long.
So I think what breaks down is just that the variances are going to 0 or are constant. So that's what's going to break down.
Just going to 0.
Yes. So there will be an upper bound. It's just maybe in some of the coordinates, the ones with the higher order graphs, as you say, that those may be just how do you say? Yeah,
and do we expect these results to hold up to the threshold of appearance of those subgraphs?
Yes. I mean, how close you can get without things breaking down, again, depends on how hard you work on this bound. and how accurate it is. But yeah.
Right. So these bounds, the moment bounds would depend on the graphon here. If you have a sparse graphon, this might become even worse.
If there are no other questions, let's go Gursharn again. So in the second half, we'll be having the hike. It starts at 2. We meet outside the Simons Institute at 2 and start at 2.
So is it going to be a random walk? Or
I think Remco has a better idea. So do you want to